Good afternoon, everyone. Thank you for being here. Um, my name is Vignesh. I'm a senior software engineer here at Google. I work in the gRPC team for over 4 years. I primarily focus on improving gRPC performance. This talk, I'll cover our experiences with the integration of IO Uring, which is a cutting-edge Linux IO API, into the high-performance gRPC-C++ stack, which is widely used for backend server-to-server communication. So this work we collaborated with a student researcher, Minwoo, who unfortunately couldn't be here in person. I'll be talking about our key takeaways based on our experiences. So before going deep into the talk, I'll cover a bit of some internals that come in handy. So at a high level, gRPC C++ relies on something called event engine, which is an internal abstraction layer. It is used to manage transfer of bytes between the client and server. So it's a public pluggable interface for low-level networking operations. And gRPC relies on event engines for several critical internal tasks, like, for example, running an internal callback, connecting to a peer, reading, writing bytes over the wire, and so on. And we have different implementations of event engine, which are platform specific. So in gRPC, like event engine is the lowermost layer, and it manages the lifecycle of TCP connections between client and servers. So gRPC C++ creates one event engine endpoint per subchannel and transfers bytes over it to the wire using that endpoint. Um, so these endpoints are typically tasked with reading, writing required number of bytes, and then invoking an internal callback after the op completes. So that's at high level what an endpoint is supposed to do. So in this talk, we are concerned primarily with the POSIX specific implementation of event engine. This is in fact the most widely used. At a high level, the POSIX event engine endpoints alternate between two phases. There is a draining phase and a polling phase. So in the draining phase, the endpoint repeatedly invokes syscalls such as send message and receive message to basically drain the socket of available resources. When the kernel reports that um, there's nothing else to do, basically, we check whether we have read enough bytes or written enough bytes. And if so, we pass along the result to the transport. If not, we enter a polling phase where we wait for more data to be available, and then we repeat this process. So this is at a high level how the TCP level endpoint works. So our goal was to improve the efficiency of these TCP endpoints. In particular, we were interested in answering two main questions. Can we reduce the number of syscalls that we actually make? Turns out like modern syscalls actually incur significant overhead. There is like privilege translation, argument validation in the kernel, there is context restoration, and so on. We are also interested in this other question: how do we improve CPU utilization? Increasingly inside Google, we are seeing workloads that consume more and more of the available memory bandwidth. Due to these memory bandwidth limitations, blocking applications until they synchronously memcopy to and from kernel buffers leads to wastage of CPU resources. So yeah, these are the two main questions that we're trying to answer, and yeah, I'll be covering a bit more on these for the rest of the talk. So we are primarily interested in studying whether IO Uring can be an answer to these problems. Let's take a step back and understand what is IO Uring. So IO Uring is a open source cutting edge Linux specific API that supports asynchronous syscalls. So at a high level, it relies on two memory map buffers. There is a submission queue, which an application can use to enqueue syscalls. And then there is a completion queue, which the kernel uses that to post completions of enqueued syscalls, and the application can read that completion queue to get notified. So typically, a user thread can enqueue a syscall into the submission queue. The kernel will consume from the head of the submission queue It'll do some async processing and then post a completion onto the completion queue. And a user thread can pop an entry from the completion queue and inspect the result of the syscall. So we were trying to see how we can use this mechanism and integrate it into gRPC. The goal was to figure out how gRPC can batch and submit syscalls asynchronously and get notified as they complete. So in our prototype, we developed an IO based event engine, and we compared the performance of the default gRPC C++ stack against one that used this custom event engine. So we implemented endpoints that can handle asynchronous send message, receive message syscalls. Our implementation relied on liburing, which is the high-level C interface to IO. In our implementation, we instantiate an IO per CPU. So the total number of IO itself is tied to the amount of CPU in the system. Endpoints get mapped to a specific IO based on the incoming CPU associated with its socket. So I'll cover a bit briefly about how a typical syscall submission workflow looks like with an IO endpoint. So the user would acquire a submission queue entry or an SQE. This, note that this does not involve a user to kernel transition. Then the user prepares this submission queue entry for submission. So this would involve setting the syscall args. And then finally, the user submits the syscall to the kernel. Now, this is the step that would involve a user to kernel transition. The liburing API is not thread safe. So we need to account for that in our implementation. And the IO submit makes one syscall to batch and submit all prepared SQEs in one shot. Now, this is a key aspect that I'll come to a bit later. So IO allows us to basically acquire multiple submission queue entries and prepare all of them and then call IO submit once. So this has the effect of batching multiple syscalls into one, thereby reducing the total number of syscalls that we make. So in our prototype, we try to leverage this feature with an implementation that relies on atomics to opportunistically batch syscalls. So multiple threads or endpoints may acquire an SQE, prepare it in parallel, and then when they all try to submit, we atomically elect one of them as the leader that can actually do the submit operation and submit all the prepared SQEs in one shot. So I talked about syscall submission. Now I'm going to talk briefly about syscall completion. So typically to get notified of a syscall completion, we register an event FD with the IO and we need to wait until the event FD is readable. Once the event FD is readable, we can read completion queue entries back from the kernel and process them to retrieve the results of the syscall. And once we are done with processing, we return the CQEs back to the IO so that it can be reused later for other syscalls. So I'll talk a bit briefly about what happened with our prototype and what the results look like. So we did some simple benchmarking. We used two machines in the same rack, each with 100 gigabit NICs. One machine was running a gRPC client and the other a server. We tested on two classes of workloads, a max QPS benchmark, which tries to generate as much data as possible, and a fixed QPS benchmark, where the load generation is fixed. We varied the number of TCP connections, request response, payload sizes, and so on. We configured the client to use our IO event engine. So first we tried a fixed low QPS benchmark. In fact, we observed a marginal regression in our latency metric. So at low QPS, memory bandwidth limitations are not the primary bottleneck. So we don't see much benefits shifting to an asynchronous syscall model. But then we increased the stress on the system. Next, we tried a max QPS benchmark, which tries to flush as much data as possible. Here we see significant gains in the QPS and median latency, as well as a significant drop in the CPU time, which is the amount of time spent in the kernel and process context. We further increase the stress on the system by increasing the number of channels to about 4K per IOU ring. So the intention was to create more endpoints that read and write data in parallel, and this increases the probability of opportunistic syscall batching. We saw that the QPS and RPC latency followed similar trends, but the number of syscalls that were submitted was reduced by about 4%. So, conclusion. So this is one of the first studies that experiments with IOU ring for a general purpose networking stack like gRPC. IOU ring was originally developed at Meta for like disk IO, and we were trying to see how it would work for a general purpose networking stack. We saw that IOU ring is not a drop-in replacement for existing ePOL based endpoints. Both of them have fundamentally different programming models. So ePOL relies on a socket readiness model, whereas IOU ring uses a syscall completion queue based model. We start to see performance gains with IOU ring when the system is stressed. There's better CPU utilization, reduction in end-to-end latencies, and an overall reduction in total number of syscalls made. In the future, we're going to experiment with some of the advanced features with IOU ring. In particular, we can reduce the total amount of memory allocated for each TCP read by using buffer pools. IOU ring allows us to register a dynamically resizable buffer pool. The kernel will auto-pick buffers from the pool to place data that is read from the socket. We also plan to explore submission queue polling mode, which eliminates syscalls entirely by having the kernel busy poll the submission queue for new entries. Now, this has the trade-off, and it may not work well for all workloads because it leads to increased CPU utilization. There are other strategies also that we are looking into to reduce syscalls, which include syscall chaining and multi-shot syscalls. So, syscalls that need to execute in a specific order can be batched and enqueued as a chain into IOU ring. Furthermore, there is this concept of multi-shot syscalls, which are just submitted once, and IOU ring can post multiple completions for one submitted syscall. So these are kind of approaches that can lead to significant benefits with in highly contended and systems which experience a lot of load. So yeah, I think that was my talk. Happy to take any questions. Yeah.
Nice presentation. I'm Chris. I work on Netty, and we also have an IOU ring implementation. So our experience is that multi-shot and buffering is where most of the performance gains are to be found. Mm-hmm. But I was curious why you use the event FD and the ePOL await as your notification mechanism as opposed to just blocking on submit.
Oh, so yeah, I think we went with that approach primarily for implementation reasons. So we have existing event engine implementations that rely on ePOL. So this made it easier to plumb our new event engine into the existing ePOL based notification mechanism that we already had for monitoring sockets. That is the primary reason why we went with this. I think we are actively exploring other socket monitoring approaches offered by IOU ring as well.
I suspect if you get rid of the event FD and just rely on submit, maybe the low connection count performance will be more on par with ePOL.
Right. Yep. It's possible.
What's the current logic to decide when we submit? Do we let the queue fill up?
We have a max batch size. So multiple threads can try to submit in parallel, and the thread that's arriving last ends up actually submitting all of the batched syscalls.
And these are across channels.
Yeah, across channels. So the more channels and endpoints you have, the higher the chance of actually batching more syscalls and submitting them.
And then I'm guessing we also have some kind of timer to say that if there haven't been more syscalls in, let's say, X milliseconds, just submit it anyway.
No, there's no timer. It's just we allow the threads to naturally race against each other, and whichever thread is like leaving last gets to submit. There's no concept of like, there's no thread which is going to run a timer and call submit periodically.
I was just imagining a case where you don't have much traffic, so you just have
Then
one.
there's basically going to be no thread which is contending, and we detect that there's no contention,
Okay.
and you just call submit immediately.
Thank you.
Do you think that after some maturity point, when it will be possible to bring a ring comparable to EPOL for the default case, it's possible? Do you think it will be possible in the future to swap to IO ring as the primary traffic layer for Linux systems?
Do I think it'll be possible to switch to IO ring entirely?
I mean, based on your experiments, like right now you put on the slide that it's not like a full replacement for EPOL. But do you think in the future it could be a replacement for EPOL?
Yeah, I think definitely IO ring offers some advanced features, which like multi-shot syscalls and buffer pooling and syscall chaining, which if we used correctly will definitely make gRPC more performant. So yeah, I think there is a case to be made. Like, yeah. Any other questions?
All of the experiments that you do right now, are they run on some Google-specific Linux kernel, or are they?
These
Okay,
experiments were run on Google specific Linux.
Okay.
But
Your
we are
experience, is it fine? Like in the public OS distributions and kernels, how good is it?
I don't think the Google specific optimizations in the kernel played a big role, because we actually don't have IO ring enabled in the Linux kernel inside Google. So these were all like just using the open source bits of IO ring. They were just merged into the kernel that we have inside. So there were no Google specific optimizations that went into this.
Thank you.
I guess no more questions.